Okay, so if you remember from last week, I'm going to scroll down a little bit here. When we're working with this Google application, which is called Colaboratory, which allows us to run Python code on Google's essentially cloud platform, after either 12 hours of continuous use or 90 minutes of idle time, the session gets restarted. So everything we did last time has been cleared out. Okay, so for example, if you click on the files icon here on the left panel, if you remember last time we made 2 new folders here, those are all gone. So we have to remake those, okay? So I'm just gonna minimize this a little bit. So let's just scroll down. So the first thing, again, we have to start at the beginning. We have to import our Python modules and packages. And the very first thing we have to do is we have to install the 2 packages that aren't part of the Google setup. So again, remember, all the actual Python code cells are this gray shading. And so to run one, you click on it, and then you'll see this little black circle with the white arrow. You click on that, and that will run the code that's in that block. And we have to run everything in order, and we have to do it one at a time. Well, actually, it's not true. You don't have to, but for this tutorial, let's do it one at a time. Okay, and when the code is in that block is finished running, you'll see a little green check mark just to the left of the block, and it'll have a little time underneath. Mine says 14 seconds, and that's the time it took to run the block. Okay, and so remember, there's a lot of errors, messages that you see. Those are just warnings that some of the packages we installed, they conflict with what's already been installed, but that's okay. That won't bother us for the tutorial, so you can just ignore those messages. Okay, so let's scroll down now, and now we have to import our modules and packages. So again, let's run that.
Hi, Amy.
Yeah, go ahead, Anna.
I'm just going to send a reminder to everybody, for those that may have not been here last week, that everybody will be, what we're doing here is following what Amy is doing in our own computers. So para los que quizás no estuvieran presentes la semana pasada, estamos todos en nuestra propia computadora, estamos siguiendo los pasos que Amy nos está indicando. Y para eso tienen que haber aceptado el link de Google Classroom que se mandó anteriormente. Gracias. Okay, go ahead.
Okay, great. Okay, so once we've imported our modules and packages, we're going to make those directories that we made last time, the new folders on the Colab instance. And this is just to help keep us organized because we're going to be downloading data files. Okay, so the first thing we're going to do is we're going to make those new files. So if I click here, and then again, if we look over here, this button here, the arrow, that will refresh the content in the file. So if we click that, we'll see now the 2 file directories that we made. So one is called ABI files, and that's for the GOZAR files, and then VIIRS files. Those are for the JPSS polar orbiting files. Okay, so last week we went through and we downloaded the VIIRS file, so I'm not going to do that again. So we're going to jump ahead and we're going to work with the GOZAR, the geostationary ABI files. Okay, and then here this block, this is just convenience. So instead of writing out every time you want to save a file or go to those directories, instead of writing out the full path like this, I just have an abbreviation. So I just name the paths to those directories just for convenience. Okay. All right. Does anybody have any questions before we go forward? Okay. Hopefully this is just a refresh from what we did last time. Okay. So remember last time we worked with what NOAA calls the NOD. That's their Open Data Dissemination Program, which is basically taking the NOAA data and it's putting it on cloud archives that are run by Amazon, Google, and Microsoft. And we're working with the one that's on the Amazon Web Services portal. And the main reason why is because there's several Python packages that make it easy to access the Amazon Web Services NOAA data. And we can do it without having to register or use a password or anything like that. So that's why I like the Amazon Web Services. Okay. So again, if we scroll down, the first thing that we need to do is we need to connect to the Amazon Web Services. And as you remember from last week, Amazon calls their cloud directories S3 buckets, and S3 stands for Simple Storage Service. Okay, so we have to do this again. We have to connect to the Amazon Web Service S3 buckets, and we do it anonymously because the NOAA data are free and open access. Okay. All right, so is everybody up to this point? Because now I'm going to skip ahead. Okay, so remember last time we did section 1, we downloaded the VIIRS data. So there's a little arrow next to section 1 here. If you just hit that arrow, it'll just collapse all the content from that section. And then what I want to do is I want to move ahead, or you can just scroll down. If you don't want to do that, you can just scroll down in the file until you come to section 2. Which is titled the NOAA GOES-R bucket. So I'll give everybody a chance to do that. So just scroll down. Okay. So what we're going to do now is we're going to look at the organization of the ABI, the Advanced Baseline Imager. That's the instrument on the GOES-R geostationary satellites that will have the aerosol and fire data that we're going to be working with. Okay, so there's 3 GOES-R satellites in orbit right now. So there's GOES-16, which is GOES East. That's the one that we're going to be working with. That's the one that has coverage over South America. And then GOES-18, which is GOES West. And then there's GOES-17, which was the previous GOES West. So GOES-17 is just in storage right now. It's not being used for operational observations, okay? But if you ever wanted any of those data, there's separate, again, what they call the S3 buckets for each of the 3 satellites. And so you can see this is the name of the one for GOES-16, and this is the name of the one for GOES-18, okay? We'll just be using the one for GOES-16, okay? Okay. So let's take a look and just see the list of all the different products that are available in the GOES-16 bucket. So again, remember we did this last time, and all we're doing is we're using the S3FS Python package, okay, and we're using the ls command, which stands for list. And so we're going to list all of the products in the GOES-16 bucket. So if we click here, we'll see them, and there's quite a few of them. So let me just scroll back up so you can look at them all. So we can see there's a whole bunch of them. The ones that start with ABI are the ones that we're interested in. That's, again, the Advanced Baseline Imager. But if you scroll down, you'll see, if we get further to the bottom here, if I can make you see that, you'll see there's some different products that begin with different abbreviations. So those are some of the different instruments that are on the GOES-16 satellites. Okay, we're not going to work with any of those, but just in case you're ever interested, the GLM, the Global Lightning Mapper, that's another one that people have a lot of interest in. So those data are available as well. Okay, so the ones we're interested in, if I scroll back up, so again, it's the names start with the sensor, the sensor name, the ABI, and then L2 stands for level 2 data. And then you'll see there's an abbreviation. It's usually 4, sometimes 5 or 6 letters afterwards. And that's an abbreviation for the actual product. So we're going to be working with the AOD data right here, okay? So the last letter, it's either going to be C or F, or there's some that are M. That stands for the observation sector. So if you remember from last week, the GOES-16 data, they have the full disk data. That's what the F stands for. And that's the whole hemispheric disk. That's the ones we're going to be working with, those files, because they have the coverage over South America. Okay. So we're going to be working with this product here, the ABI L2 AODF. And then the VIIRS products, let me come down here and find it. This is the VIIRS product for the full disk. So the abbreviation is FDCF. Okay. So we'll see that. We're going to see examples of that as we go along. Okay. All right. Oh, and I think I forgot to mention, let me scroll back up. So usually what I do when I'm printing out information from directory paths is I don't want the full path. I just want the last part of it, which in this case is the product name. But I just wanted to prove to you here in this product that we actually are retrieving the full directory path. So which in this case is the satellite and then the product name. Okay, so all I did was print out the product names, and that was just for clarity. All right. Okay, does anybody have any, look in the chat, any questions? Okay, great. So what we're going to need to do, of course, is we're going to need to navigate through this S3 bucket to find the specific files that we're interested in. Okay, and so again, our case study day is November 6th, 2023. So we want to be able to go and find the files for November 6th, 2023. And to start off with, we're just going to work with 1 hour of files. So we're going to pick the files from in the morning from 1300 to 1359 UTC. Okay. So in terms of the organizational structure, so you already saw the products. Then they're organized by year, the 3-digit Julian day, the hour, and then the file name. Okay. So again, we will string that all together to find the files that we want. So in this example, you can see this is the satellite NOAA 16. This is the product name. This is a CONUS sector AOD file from 2023, Julian day 344, hour 17. And then this is one of those files in that particular folder. Okay. So this is what we're going to do. We're going to basically put this whole directory path together to get the files that we want. Okay, so before we do that though, if you remember from last week, the ABI data files are organized, they're named using the Julian day instead of the month and date. So that means if we're going to be searching for files, we have to know what the Julian day is for our observation day of interest. So again, we're looking at November 6th, 2023. So just this little code here, all it does is if you enter the year, the month, and the day as integers, it will return the Julian day for you for that particular day. So if we run this, we'll see that for November 6th, 2023, the Julian day is number 310, and this is actually returning it. This code is returning the day as a string. Okay, and that's going to be important for the next step. All right. Okay, does anybody have any questions about that? So basically this little code here, this line right here, basically makes it so that we don't have to go somewhere and look up the Julian day on our own. We can just type in the year, the month, and the day into our code, and then it'll convert to the Julian day for us. It's just a convenience. Okay. All right, so now I promised you we were going to look for files that were for November 6, 2023, from 1300 to 1359 UTC. Okay, so let's start with the VIIRS files. So again, the abbreviation for the VIIRS files is FDC. Okay, all of the products have these 3 or 4 letter abbreviations. Okay, excuse me. So let me scroll down here. So this should look very similar to what we did last week. Okay, we're essentially doing exactly the same thing. The main difference is that we're searching in a different bucket. So we're searching for the geostationary files instead of the polar orbiting files. And then we also have to do this extra step where we have the Julian day. Okay. So we're going to basically put together the directory path to get us to the Go16 full disk VIIRS product for November 6th, 2023. And we want all the files, again, for hour 13, which is going to give us the files from 1300 to 1359 UTC. Okay. And so we're going to use that code we just saw to calculate the Julian day. And then we're going to use the S3FS package to grab all those file names. And then we're going to print them out. Okay, and again, I just want to print the file name itself, so I'm printing the last part of that directory path. And then we can also use the fs size function. We used this last week to give us the approximate file size. So I'm going to run this now. And the reason why is before I download anything, I like to know how big the files are before I download them. Okay. And the other thing is that for the full disk files, again, if you remember from the slides last week, in most of the time, there are observations every 10 minutes. So we only have 6 files in an hour. So it's a little bit more manageable than the polar orbiting files, which of course have global coverage. So they have over 500 or 1,000 files in the individual bucket that we're looking at.
Hi, Amy.
Yeah.
We have a question. I have a comment. Can we remind everybody what a full disk sector is? And then there is a question in the chat. Please, what is the product name for ultraviolet radiation?
Okay, hold on. So let's answer that in order.
Okay, thank you.
So I don't get confused, no problem. Okay. Whoops, sorry, that was not the right one I wanted. I want the scan sectors. Okay, so this is, can you guys see that web page? So this is the full disk sector, okay, for GO16. So it has, it's the full hemispheric disk, and so it includes South America. Okay, so that the full disk files will have data that cover this entire area. Okay. And then the second question was the product name for ultraviolet radiation. So I don't, you know what? I'm not familiar with that product. If we go back, I know there is, so there's a UV sensor. It's this one, it's the SUVI. So it looks like they're all level 1B files. So I'm honestly not familiar with this product, but I can find out some information for you if you're interested. Okay, any other questions? Those are good questions. Okay. All right, so going back here where we printed out our 6 files and the file sizes, you can see the VIIRS files. They're not that big, okay? So they're maybe 2 to 3, these are close to 3 megabytes per file. That's pretty small. But when we get to the AOD files, those are a lot bigger. So, and again, I want to prove to you that what we're actually finding is the full directory path. But again, we put this together ourselves when we did the search. So we already know all that information. What we're really interested in are the file names and the file sizes. Okay. All right. So now that we found our 6 files, we can download them. So again, this is exactly the same as what we did last week. We're using this fs.get function, and then we have the file name, and we're saving it to that ABI path that we set, and that's going to put the files that we download in this ABI files directory that we made on the Colab instance. Okay, so if we run that, it should be pretty quick. Yeah, it's really quick. And then if you go back up to the ABI files here, and you click on that, let me expand this a little bit, you should see them. There they are. So those are the 6 files, right? 1, 2, 3, 4, 5, 6 that we just downloaded. Okay. And again, I don't know if you guys can see here, but if you look at the file name, so again, the file name has a lot of information. So it's telling you, again, this is the abbreviation for the ABI level 2, and this is the FDC, the VIIRS product. The F stands for the full disk. M6 is the scan mode. M6 is the what they call the routine mode. That's what happens most often. And then it's the GO16 satellite, and this is the starting, ending, and creation time for the file. And so again, the way you look at the start and end times, it's the year 2023, the Julian day. In this case, it's Julian day 310, and then the time in UTC. So this is 1300 UTC. Okay. Somebody had a question. Is it possible to download these in Google Earth Engine?
To do this, is it possible to do the same process that you're doing in Google Earth Engine?
Yeah, so the data are on Google Earth Engine. The problem is that there aren't as far as I know, there aren't as many Python packages that allow you to do this searching step. So it's a lot harder to find and search for the files that you need. So you can do it on Google Earth Engine. And if you're if you're used to Google Earth Engine and you have a Google account, then I think there's more resources available to you. But if you want a free way, like free and open access, there's more flexibility and it's easier to search for the files and download the files using the Amazon Web Services interface. Yeah, that's a good question. Okay, and that's why I use the Amazon, and I teach the Amazon Earth interfaces, or Amazon Web Services, excuse me, interface. Okay. All right, did everybody download the files? Everybody good? They have their 6 files? Okay, so now I want you guys to do exactly the same thing, what we just did. So search for the files for November 6th from 1300 to 1359 UTC, list the files and their sizes, okay, and then download the files. So it's everything that we just did. The only difference is that you're going to change the name of the product. So the product bucket, instead of being, or no, let's go back up here. So instead of the product bucket being this one for the VIIRS, the FDCF, you're going to instead use the abbreviation for the AOD, which is the ABI Level 2 AODF, okay? So why don't you guys, so in these 2 empty blocks here, why doesn't everybody take a minute and see if you can search for first and then download those 6 aerosol optical depth files. And if you get stuck, the answer is right here, but try to do it on your own first. Just take a minute and then I'll go over it. So it will take longer to download the AOD files than I did the VIIRS files because they're larger. I think it's going to take maybe 20 or 30 seconds. So don't let that concern you. Okay. All right. Do people get it to work? Yes. Okay. I see a thumbs up. Great. Okay. So hopefully everybody had a chance to. So again, all you really need to do is you can, you can, again, look down here. Whoops, I click on it. This has the answers here. But really all we need to do is just copy and paste. So we can take this, we can copy it and put it down here. Okay. And then I guess I need to copy the comments again. I can take those out. And then here, this is what we need to change. So we want to make this, instead of FDC, we want it to be AOD. Okay. So then if we run this now, so again, we get the 6 files, and they're going to have the same file times, but we can see now they're the AOD files, and the file sizes are much larger. Okay, so they're anywhere between about 30 to 35 megabytes. Okay, compared to about 3 megabytes for the VIIRS files. Okay, and so then to download, again, we can just copy this code here, put it down here. And since we kept this same, we kept this same command, we called the AOD files that by the same variable name files, we can just use this exact same code. We don't have to change anything. So if we run this and then we refresh, we should see, oh, it only took 2 seconds. Oh, that was fast. Okay. When I did this before, it definitely took longer. So maybe, I don't know, there was a lot of traffic on my website or something. So we can see them here, hopefully the top, 1, 2, 3, 4, 5, 6, and there they are. Okay. All right, does anybody have any questions? Is everybody able to get that to work? Okay.
Amy, perhaps,
Yes.
I mean, I hope it's clear for everybody why we're looking at these 2 types of files, right? There's the AOD and then there is the FDCF file, right? Or maybe Amy, if you don't mind explaining what's the difference and why we're looking at those 2.
Sure. So again, the focus of our training is going to be on the aerosols, smoke and fires. So the aerosol optical depth file is going to give us the information about the aerosols associated with the smoke. And I'm going to have some slides when we're done with this, finishing up with week 1, that I'll talk more about, what aerosol optical depth is. And then the FDC, the VIIRS file, will give us the information on the satellite sense locations of the fires, and also a product called fire radiative power, which is a measure of the intensity of the fires. So that's why we're downloading these 2 types of level 2 products, because we're going to, next week and then in week 4, we're going to actually, work with these specific data files. But the first step, anytime you work with a satellite product, is you have to actually either download or access the file somehow. So that's why I want to show you. That's why in week 1 and finishing up today, I need to show you how to actually access the files. Okay. Anybody else have any questions?
¿Alguna pregunta más para Amy antes de que pasemos a la siguiente parte?
Okay. So I should mention too is in week 3 and 4, what we're going to do is we're going to actually start by, so week 3, next week, we're going to work with the VIIRS files, the polar orbiting data files. And then in week 4, we're going to work with the geostationary files, the ABI files, the ones that we just did. And so at the beginning of both of those weeks, we're going to re-download the files. But we're going to go through it really quickly because we went through it today. So if you have any questions, let's definitely clear them up today. Okay. Anna, can you translate the question from Lionel?
Yes. How could you download the archive in NetCDF in another format, for example, to be able to read it in Excel?
You can't. That's the problem. You can't. So what we could do with, for example, the VIIRS files, you can take the information out of the NetCDF file and put it in Excel, but you can't open a NetCDF file in a format like with Excel, unfortunately. Yeah, that's kind of the whole point of this training, is that if you want to work with the satellite files, you have to be able to work with the NetCDF files.
Right, but once you read the data, you could import it into Excel.
Yes. Yes.
No directamente. Entonces la respuesta es que no se puede leer directamente con Excel o bajar.
Pero además creo que sería un archivo súper grande, ¿no? Sería muy poco práctico, me parece, no sé.
Sí.
I mean, I guess the Excel file would be very big to be read by Excel, right? I mean, maybe it can read it, but I don't think it's going to be practical to manage the data with Excel. What do you think?
Well, so again, it depends. With the VIIRS data, it's not too bad because with VIIRS, it's just the latitude and longitude which is the fire detections. And then if you want FRP, then it's just another, column with that value. So that's pretty easy. The aerosol optical depth data, it's a little more difficult because they're two-dimensional files or two-dimensional data arrays. So you would have to, again, process them somehow. Let's say you wanted the AOD for at certain points, certain latitude and longitude points. You'd have to do some processing, and then you could export that information to an Excel file, which would be manageable. Yeah, I mean, technically it would be a CSV file, but you can open the CSV file in Excel.
There's a couple other questions in the chat that just came in.
Okay. Is it possible to download specific areas using a shapefile? No, unfortunately. So what we're going to do next is we're going to actually download specific areas. Okay. So maybe that will, Gerson, maybe that will answer your question. But we're going to do it as a net. Basically what we're going to do is we're going to make a new net CDF file, but it's just going to have the area corresponding to Central, Western, South America. Okay, so let's do the next section, and if you still have a question, then let's circle back and we can follow up. Okay, and the next question is: GOES used to monitor air quality? Not directly, but it's used the aerosol optical depth, which is what we're going to work with, because it's quantitative. It corresponds to the concentrations or the number of aerosols or particles in the atmosphere. It can be correlated with surface air quality. So it's used to monitor air quality in the sense that we can get information about the surface from it, but it's always going to be an estimate because, again, remember, the satellites are measuring the full vertical column of the atmosphere. So they're not directly measuring the air quality at the surface. Do you want to add anything to that, Anna?
Yeah, I just added that it's not the same as PM 2.5.
Okay.
No es lo mismo que PM 2.5, ¿no? Como dije en la sesión anterior, es la cantidad total de aerosol en una columna entre la superficie de la Tierra y el instrumento satelital. Y puede, o sea, si la contaminación o los aerosoles están predominantemente localizados a nivel de superficie, entonces si el aerosol optical depth sí que puede ser indicativo de la calidad del aire a nivel de superficie. Okay, thanks,
Okay,
Amy.
Sure. Any other questions? Yeah, everybody's asking great questions. Okay. Yeah, I should mention, there were a couple of questions about, using Excel or a shapefile. Those are very popular questions. The biggest hurdle to using satellite data is the fact that they're net CDF files. And so you have to use something like, like a programming language like Python, or there's special tools like NASA has a tool called Panoply. You have to do something different to work with them as opposed to just being able to open them, in Excel or, some other common software package. So yeah, I understand it's definitely, it's a challenge, but hopefully after you're done with the training, you'll feel more comfortable working with the net CDF files. Okay, so let's move on. This is the last section of week 1. So let's see, I forget who it was. Gerson, I guess, asked about whether, to download specific areas from the file. So I really wanted to address that because if you remember, the full disk files, they're covering this whole area of the hemispheric disk, including all of North America and Central America. So if you're in South America, you don't really need any of that information. You just want to focus on, in our case, the part of South America that's of interest to you. So we're going to focus on roughly this area here in Central Western South America. Okay, so what I did is I wrote a function so that essentially what we can do is we can take the original files, the full disk files, and we can just pull out the part of the file that corresponds to the region that we're interested in. Okay, and so it's a little bit tricky to explain because if you remember from last week, because the GOES 16, the GOES East satellite, it's always in the same location. So the data, the domain doesn't ever change. So because of that, in these data files that we downloaded, and you'll see this when we open one up next week, or no, sorry, in 2 weeks. The files themselves, they don't include latitude and longitude inside. Okay, and the reason why is because you can calculate latitude and longitude. And so the GOES-R program, they have a very thick, long user's guide here, and they have information in there that will allow you to calculate the latitude and longitude using the information in the file. And the main variables that are in the file that we need to use are called X and Y. Those are variables, okay? So X is, I think I put up here, yeah, X is the east-west scanning angle, and Y is the north-south elevation angle of the satellite, okay? You don't need to know that. All you need to remember is that you use X and Y and some different constants that describe the geostationary satellite position to calculate latitude and longitude, and we're going to do that. But what we want to do basically is we want to go backwards. We want to say we have a certain latitude and longitude corners of the domain, and we want to use those latitude and longitude corners to subset the file using the X and Y values. Okay, so that's what this first function does, and let's just run it here. So what this first function does is essentially it allows us to say, we're going to say a specific latitude and longitude, and what we're going to get out at the end is we're going to get out these two very complicated equations that tell us what these Y and X coordinates are, okay? And so once we have those Y and X coordinates, let me scroll down a little bit more. There's a lot of text here. So once we have those Y and X coordinates, we're going to be able to use those to subset the data in that whole big full disk file, okay? So the first thing we're going to do is at the top is this is where we're going to enter the coordinates in latitude and longitude for the domain, just the smaller geographic area that we want to pull out of the file, okay? So what we're doing is we're going from -5 degrees latitude to -30 degrees latitude, and then from -80 degrees longitude to -45 degrees longitude, okay? Those are the corners of the region that we're going to subset in South America, okay? And then what the rest of the code does, scroll down, get a little bit. So a couple of things I want to point out. So first thing it's going to do is it's going to grab, we're going to do this for the AOD files. So the code is going to grab the 6 files here, AOD files that we downloaded, okay? And it's going to go through one by one. And so for each one, oh no, I'm sorry. Nope, I'm sorry, I apologize. I forgot what I did. Never mind. It's not going to do that. Because what I wanted to show you what to do is instead I wanted to show you how to open a file remotely, okay? So we downloaded files, but if instead you use the fs open command, okay, that will open the file remotely on the Amazon Web Services server, okay? And so we can open it, and we're just going to call it remote file, and then we're going to use the Xarray package, this command here, to open up that remote file, okay? So we're not going to download it. We're going to just open it up and pull out the information. Okay, so again, I'll show you further examples of this, but I just wanted to give you an example of how if you don't want to download the files, you actually can open them remotely. Okay, and so when we do that, we're going to use that function I just defined to find the latitude and longitude that we entered, those domain corners up here, right here. We're going to convert those to those X and Y variables, okay, that I mentioned. And then once we have the X and Y values, we're going to use them to figure out the index in the data array in the file. And so once we have, and that's what this is doing right here. And then once we have those indices, we're going to use the xarray iSelect function, and we're going to slice all of the data in the full disk file so that it just corresponds to that geographic range we set. Okay, and that's what this does right here. Somebody last week asked about this this iSelect or the select command in xarray. So I forget who that person was, but we're going to use it right now. Okay. And then all this section does here is we're just going to change the metadata in the file so that when somebody opens the file, like you open it later, you'll remember what you did. Okay. We're basically just saying we're changing the information in the file of where the latitude, longitude corners are. And then we're adding here, we're adding a comment that we've basically done that, okay, that we've subsetted from the full disk file using the indices for X and Y that we found, okay? And again, the idea with that is you want to add some metadata so that you know when you open this file up what happened, like what did you do to generate, all right? And then the last step here is we're going to save the file, okay? And we're going to save it to the same ABI files. So let's run this. And this is going to take a minute. So if you scroll down, so what I'm having to do first is that as it goes through, there's going to be 6 files. And so as it's processing them, I'm having it print out the file name that it's working with, just so that we can keep track. Okay, so it's done with the first one. So if we go back here and we refresh, so we'll see we've got, let me see if I can make this a little bit bigger. So here's our new files. And so what I did too when I saved them is I changed the file name. I just added subsetted to the beginning of the file name. Again, that way it's easy to know which ones are in this case, the original files up here. And then these are the ones, I can refresh it, we've got some more. These are the ones down here that we've subsetted. Okay.
Amy, yeah, I'm just going to explain what the word.
Yeah, you want to explain that in Spanish? Okay.
Yeah, so subset significa extraer de lo que es el archivo completo, ¿no? De que incluye toda la región de Norteamérica, Centroamérica y Suramérica. Y en estos archivos que pone subset ya hemos extraído de ese archivo solo la región que nos interesa, que es una región, es Bolivia y parte de Perú. Y esa región está indicada por la latitud y la longitud que indicó Amy anteriormente. Y entonces así es posible trabajar con un archivo que es más pequeño porque tiene solo la información que necesitamos y no tenemos que trabajar con el archivo grande que contiene todo el sector, el full disk. Okay, yeah, I just explained that what's the subset.
Great, thank you. And so again, the reason to do this is so that if you are going to download the files, you're downloading much smaller files. So it'll take up less space, and it'll when you actually work with the files, everything will be much faster because you just have smaller files that just contain the data that you're interested in.
¿Alguna otra pregunta respecto a esta parte de subsetting? Y si no les importa indicarnos si lograron conseguir estos archivos subsetted como ha hecho Amy, si nos importa indicarles con un thumbs up o ponerlo en el chat, así sabemos más o menos si estáis siguiendo.
Yeah, there's a couple questions that just popped up, Anna, in Spanish.
Is it necessary to do a geometric calibration or other correction to the downloaded raster files?
No. No, everything is in the file, and we'll see how to pull that out in 2 weeks when we work with the ABI files. Okay, it looks like some people did it.
Mm-hmm.
Can you ask?
Yeah, for each day, do the X's and the Y's change?
No, they do not change.
Right.
Yeah.
Recuerden que estamos trabajando con datos geoestacionarios del instrumento ABI del GOES, entonces cada día son iguales. Cuando trabajemos con el instrumento VIIRS, esos sí cambian, pero los productos del GOES no cambian.
Yeah, so this is always, this is the same area. So the individual grid with the ABI, the little pixels that are 2 kilometers by 2 kilometers, they never change. They're always the same.
Entonces, si recuerdan, el satélite está posicionado siempre sobre el mismo lugar de la Tierra. Y entonces está lo que son las cuadrículas, cada día no, la longitud y la latitud de las cuadrículas no cambia de un día para otro. Por esa razón no están incluidas esa información en los archivos, pero se puede generar, como ya nos ha enseñado Amy. Okay, I don't see another question.
Karen answered Diego's question too. That's good. Okay. Anybody else have questions? Okay, I think this will make more sense also when we get to week 4 and we start working with the ABI data. We can plot the data. Then you can see what the data look like. Visualization is always helpful. Okay. Oh, sorry. I thought that's Karen's comment. I thought there was another question. Okay. Okay. So we're done with week 1 now. So now everybody should know how to find the VIIRS data and then download them, and find the ABI data and download them, and if you want, to subset them. Okay. All right. So so you can close up this first week 1 if you want. I'm just going to minimize it. And then I have, so now we're going to go to week 2. I actually have some slides. So I was thinking, I only have, I think there's only 16 slides. There's not very many. So this will take, I don't know, maybe 15 or 20 minutes, and then we can take a break after that. How does that sound?
Sounds good, Amy. Thank you.
Sound good? Okay. Okay. So last week we talked about the ABI and the VIIRS sensors in general. And so today I just wanted to talk, give a few specifics about the aerosol optical depth and the VIIRS data files, since those are the files that we'll be working with next week and the week after. And I should mention, I'm a member of the NOAA aerosols science team, so I know much more about the AOD product. I am not a member of the VIIRS team. I know a fair amount about the VIIRS files, but if there are any specific questions, you'll have to let me know, and then I can always talk to the VIIRS team and get the specific answers for you. Okay. So let's talk about AOD first. So aerosol optical depth, it's a measure of the extinction of radiation by aerosols in the atmosphere caused by absorption and scattering. And so it's a function of wavelength. So the data we're going to work with from ABI and VIIRS, aerosol optical depth is reported at 550 nanometers. So right in the middle of the visible spectrum of light. And so we have to talk about the algorithm a little bit, just so you understand, when we work with the data themselves, how to actually process the data so that, we can understand what the aerosol optical depth measurement is. So the algorithm, it's a formula that is used to calculate, or we say retrieve AOD. So again, AOD is a level 2 product. So it uses what's called the level 1B data, and those are the spectral bands from the ABI and the VIIRS sensor. So you can see, let me change to the laser pointer. So you can see the table at the top These are the ABI bands that are used in the AOD algorithm, and then the table at the bottom are the VIIRS bands that are used in the AOD algorithms. And so there's separate AOD algorithms for retrieval over land and over water. And there's also what are called internal tests. And so internal tests, it's this last bullet here, they screen for unfavorable conditions. So either where it's difficult or where it's impossible to measure AOD. And I'll talk a little bit more about that in the next slide, okay? So those different tests, they help provide information about the AOD, and it's called a quality flag. So the quality flag, there's lots of different quality flags, but the overall quality flag, that's the one we're going to work with. It expresses the confidence in the retrieval or the measurement of AOD, okay? So this figure has an example of, again, the full disk, GOES 16 ABI AOD quality flags. It's this different shading, the green and the blue in the brown shading. And so the thing to remember is that there's technically 4 quality flags, but there's high quality AOD, medium quality AOD, and low quality AOD. So high quality is the most accurate, of course, and it should be used for any sort of quantitative application like numerical modeling or data assimilation. But the flags, the screening is extremely stringent. So there's still a lot of like accurate AOD that gets screened out. So that's why if you're doing any sort of qualitative application, like weather forecasting or air quality forecasting, you can also use the medium quality AOD. Okay, it still has, there's some uncertainty, but it still has a lot of accuracy associated with it. But the low quality, that has high uncertainty. And I'll show you some examples in a second. So you want to generally avoid using the low quality AOD, okay? And then the areas where AOD isn't retrieved, where anywhere there's a cloud, snow or ice on the surface. For the ABI original, which is called the baseline algorithm, any sort of bright land surface, and I'll talk more about what this means in a few slides. Anywhere where there's sun glint, so sun glint is a measurement artifact, and it occurs when sunlight reflects off a body of water, like an ocean or a large lake. And so when that happens, that very reflective area, there's no AOD measured there. And then, of course, at nighttime, AOD is only a daytime observation when it's at 550 nanometers. So again, these green areas just show some different examples of where you have low quality. And then the brown is where there's no retrieval. And the big one is this dark brown. This is an area of sun glint. So again, this is where the sun is reflecting off the ocean at the same angle that the ABI sensor is looking at the surface. Okay. All right, so just some examples of low, medium, and high quality AOD. So this is from the GOES West satellite. This is from December 2020. And so there were fires burning near Los Angeles, California, and then the smoke plume went out over the surface of the Pacific Ocean. So this is the high quality data. So you can see there's a lot of gaps. So there's gaps along the coastlines. There's holes over some of the area where the smoke is. So this is the most accurate AOD, but you can see there's definitely some missing areas, and that's because as I said, the screening is extremely stringent. So now if we add in, so again, I'll go back. So this was high, this is high plus medium. So you can see how a lot of that smoke plume is filled in, and then a lot of the areas along the coastlines, and then some of the areas inland as well. So like this here inland, that's smoke from the fires were right about in this area. So you can see the advantages of adding the medium quality because we get most of the smoke plume now, and then we get a lot of this information on land as well. So now if we look at the low quality, we add that in. So again, this is high and medium, and this is the low quality. So you can see, we have a lot more coverage, but there's a lot of all this, this red shading, the high AOD, along the coastlines, hopefully you can see here, and along down here, that's erroneous. So those are not real measurements. Like that's not really high AOD. that's essentially an artifact. So that's why you don't want to use the low quality most of the time, because you get these artifacts, this artificially high AOD. Okay, so essentially the bottom line is that you want to make sure you use the quality flags to process the AOD, and I'm going to show you how to do that. Okay, I just wanted to briefly mention the validation. So NOAA has requirements for aerosol optical depth. So both for the GOES 16, the ABI, and then the VIIRS aerosol optical depth, they have to meet requirements for accuracy and for precision. Okay, and so the way that the AOD data are validated is using AeroNet AOD. AeroNet is a global network of sun photometers. So they're instruments that are on the surface of the Earth looking up, measuring AOD. Okay, and then the satellite AOD looking down that's how the data are validated. Okay, and so the thing to know from these is basically that the AOD is meeting the requirements for precision and accuracy, and that the ABI AOD is capturing the diurnal variability that's seen during the course of the day from the AeroNet data. Okay, so I need to mention that starting earlier this year, on February 6th, the ABI AOD algorithm, it changed. So the old algorithm was called the baseline, and it was updated to what's called the enterprise algorithm. Okay, and the advantage of the enterprise algorithm is that you can use essentially the same algorithm for the ABI geostationary data that's used for the VIIRS polar orbiting data. Okay, and that's just good because it improves the consistency in the way that the AOD is measured from the polar orbiting and the geostationary data. Okay, so there's some advantages with the enterprise algorithm. So the baseline doesn't make retrievals over bright land like deserts, but the enterprise algorithm does. And then the enterprise algorithm also is able to estimate AOD in what is called heavy aerosols. So for example, like areas where there's really thick smoke, the baseline just couldn't handle that. So the enterprise algorithm has increased in spatial coverage because it's more high quality AOD retrievals. Okay, so in terms of the accuracy and precision, the performance is very similar, and the enterprise AOD is meeting those requirements for accuracy and precision. So the implications for you is that there's going to be fewer high AOD retrievals over the Andes region. In 2 weeks, when we look at our case study, we're working with data from 2023 before this algorithm change happened. So you're going to see there's an area of high AOD over the Andes, which is anomalous. It's not real. Okay, so that is much reduced now with the enterprise algorithm. And then also where there's very thick smoke, there's going to be more AOD retrievals now than there used to be.
Hi, Amy. I'm going to go over that again, that last part, because I think it's super important. Entonces, el algoritmo, y recuerden que con el algoritmo nos referimos a el proceso de ecuaciones y estimaciones para convertir lo que ha detectado el satélite en una cantidad geofísica, ¿no? Como puede ser el aerosol optical depth o como puede ser la detección de los incendios. Entonces, en el caso de los aerosoles, en el algoritmo actual, a veces cuando decimos anomalously high AOD, nos referimos a zonas donde los aerosoles, el satélite los muestra como elevados, pero no es real, es un error esencialmente del algoritmo. Y entonces, en esta nueva versión del algoritmo Enterprise, se corrigen algunos de estos errores y entonces tenemos un producto mejor, ¿no? Tenemos un producto más fiable y además tenemos más datos de aerosoles donde hay humo muy, muy, muy denso. Entonces es una mejora en lo que llamamos el algoritmo. Okay, thanks, Amy.
Yeah, thank you. And then this table just.
Sorry.
Oh, sorry, Marcos, did you have a question?
Yes, could you go back to your
Certainly.
slide? When you say improves consistency, what exactly you mean? That's a curiosity.
Well, So NOAA wants to essentially have one set of algorithms that can be applied to all the different sensors. And the only difference being that, each of the different sensors will have slightly different wavelength channels and, in terms of the availability of their observations, but then everything else about the algorithms will be the same. The physics, the processing.
I see.
So,
Okay.
so the idea being that, if you wanted to try to combine, and there's a big push to do this, combine observations from the polar orbiting and the geostationary satellites, that, it'll make more sense if you're trying to blend them, for example, if they're made using the same algorithm. That's what consistency means. Just the physics and the algorithm processing being essentially the same between the ABI and the VIIRS just makes it easier to analyze the data if you're comparing them.
Fantastic. One more thing related to one of the questions that is on the chat. One of the main reasons why we could have anomalous values or not the best data is usually cloudiness, right?
Yes.
That's one issue. But in the past, at least with a MODIS instrument, I remember once that Lorraine Romer was giving a talk, and it was very clear when you look at the data that there was some kind of a strange thing over the Andes. And they said that they have some problems because the altitude of the Andes. Do you know if there is any problem with the algorithm in this region? Because there is one question also related to if there is any processing or pre-processing that we should do to correct the anomalous values over the Cordillera. That's what the question says.
Oh, well, so I would say, for the baseline algorithm before February 26th, I don't think that you can use the AOD over the Andes because they had this anomalously high values. I could ask my group if you could correct them, but I don't know, just because it's such a bright surface. But that anomaly is much reduced with the enterprise retrievals.
I guess it's part of the research that we have to do. I mean, first in a scientific framework, and then to move this into the operational mode, I guess, in the future, right?
Yeah, if that's something that we could collaborate with, I think that would be great.
Okay.
Yeah, so the specific question is, so with the enterprise algorithm, I assume that it means here, Christian has this question. So is there special processing that is being done by the new algorithm to fix the anomalies over the Andes? And I think the answer is yes, right?
Yes. So it's not specifically over the Andes, like specifically the Andes. It's all bright surfaces. And so because the Andes is bright, then that is why that because in the baseline there isn't that retrieval over bright surfaces. So the enterprise algorithm is addressing that.
How about the altitude issue? Is that part of the issue? Altitude, or is there most?
I've never heard of an altitude issue, so I'd have to talk to my group about that.
Okay, thanks. Yeah, it might be with the trace gases I'm thinking about. I know with the trace gases it is an issue, like the NO2, for example.
Okay.
But thank you. Yeah.
Sure.
Great.
No problem. So this is just for reference. So this is the main one, the retrieval over bright land, and then the heavy aerosol callback. So those are two aspects that weren't available with the baseline algorithm, but that are available with the enterprise algorithm. That I think are going to make that you're going to notice a big difference in the South America, Central, Western South America region. Okay. So switching now to the VIIRS polar orbiting. So again, VIIRS has the same requirements for accuracy and precision, and VIIRS is also validated using the ARNet AOD. And so this is just showing the validation for the VIIRS on the three different satellites, SMPP, NOAA 20, and NOAA 21. And so you'll notice there's a lot fewer matchups available for NOAA 21 just because it's been operational for a much shorter time period. So, but the thing to notice is that, again, there's a very close to 1-to-1 ratio between the VIIRS AOD and the ARNet AOD, and the bias and the root mean square error are quite low. And this is over land, and then the same thing over water. Okay, again, there's fewer matchups over water because there's fewer ARNet stations over the water versus land. Okay. So I mentioned this before. So even with VIIRS that has this heavy aerosol callback, there still can be locations where the smoke is so thick. This is an example from the northwestern United States in September of 2020 when there were very big wildfires burning. And so this kind of like dark, almost brownish color to the smoke. The part of the AOD algorithm is there's a cloud mask that's a separate product that's generated using separate algorithm, and the AOD algorithms read in that cloud mask. And so if the cloud mask thinks that this thick smoke is a cloud, that automatically triggers the AOD algorithm to not calculate AOD in that area. And so that can happen with these really thick smoke plumes. So sometimes you can see gaps in AOD where there's no retrieval, and it's caused by this upstream cloud mask. Okay, so I just want to mention that. That's another artifact or issue that you just have to be aware of when you're using aerosol optical depth. Okay. And this is the final slide about aerosol optical depth. So this has a lot of information on it. And next week, when we talk about the VIIRS aerosol optical depth, we'll start talking about some of this information. But I just kind of wanted to summarize the availability and so AOD is available from both of the GOES 16 satellite, or excuse me, GOES R satellites, and then all 3 of the polar orbiting satellites. For both ABI and VIIRS, the valid range of the ABI data is minus 0.05 to 5. Okay, you'll notice that AOD doesn't have units, it's unitless. Typically, values will range from 0 to 1. So when we plot the AOD data, we're going to use a range from 0 to 1. And then we'll indicate, actually, we're gonna look at this in the Python tutorial this afternoon, or later when we're done with this. We're going to use a separate color to indicate aerosols that have AOD greater than 1 up to 5, just to highlight those very thick aerosols. Okay, so you might be wondering, how can AOD, which is a physical measurement of aerosol number or concentration, how can it be negative? So the negative values, they indicate the uncertainty in the AOD retrieval. Okay, so again, this is it's a very complicated calculation essentially that's happening, and so there is some small uncertainty. So when we think about the negative values, just think about them as very, very small positive AOD. And when we plot them, we're going to plot them the same color as essentially 0 or those very, very small AOD values. Does somebody have a question? From Javier? Anna, could you read that for me, please, from Javier?
I am also here. It says, okay, in the validation, do we need to evaluate the correction of bias? I think it's what he's saying.
No, you don't have to worry about that. It's very small. And again, the point I just wanted to make is that NOAA has requirements for the AOD value, because every measurement is going to have some sort of small bias or error. And so I just wanted to demonstrate that both the ABI and the VIIRS AOD are meeting those requirements.
And there is another question from Anna. It says, which one has better resolution?
Maybe spatial resolution? Is that what Anna means? So if it's spatial resolution, Anna, so this table here talks about that. So the VIIRS data have higher spatial resolution. They have 750 meter resolution, whereas the ABI AOD is 2 kilometer resolution. Okay, the difference is, again, the trade-off is that with the VIIRS, the polar orbiting satellite, you only get 1 observation per day, 1 from each of the 3 VIIRS on each of the 3 satellites, and they're all in the early afternoon. Okay, whereas the ABI, you get observations every 10 minutes during daylight. So that's the trade-off between the spatial resolution and then what's called the temporal resolution, or the frequency of the observations. Okay. All right, so we talked about the uncertainty. We talked about the data range. What else? Oh, the coverage is going to be different. You guys remember that. So the VIIRS data have global coverage, and the ABI data just have the coverage over the Western Hemisphere. And then I just listed the dates when the data are available, or became available. Okay, so just so you have that as a reference. Okay. Anybody have any questions about AOD before we switch to VIIRS? Again, once we start working with the data, people might have more questions, and you can actually kind of see what a file looks like and think about can monitoring be done at night? So for VIIRS, yes, but for AOD, no. And the reason why is because the AOD is measured at 550 nanometers, which is in the middle of the visible spectrum. So you need visible light, which of course we don't have at night. There is actually some research trying to use moonlight to retrieve AOD at nighttime, but it's it's still very experimental. Yeah, so there aren't any operational products. Yeah, but that's a good question. Because a lot of things happen at night, fires, for example. But, okay. Oh, Anna. Okay, Anna was just answering that. Okay, great. Okay, so we just have a few slides about VIIRS. So again, these are from my colleagues, from Ivan Cizizar and then Chris Schmidt. So I just wanted to, touch on a few things that we're going to work with. So when we actually work with the fire data, we're going to work with the fire detections, and that's an example on the top here. So this is data from a fire that was in California back in, when was this, 2021. It was called the Caldor fire. And so these dots here, these are fire detections, which are just indicating the location, the latitude and longitude of the fire sensed by the satellite. And then this is the same thing, but this is the fire radiative power. Okay, and so you can see the equation for fire radiative power. Basically, the thing to remember is that it's a measure of the intensity of the fire. So it can help show you where the most intense burning is. It's also used by modelers. They assimilate fire radiative power to give an idea of the emissions into the atmosphere, or the height of the smoke, the plume rise into the atmosphere. That's used in models a lot. So with this example, the higher values of fire radiative power are colored kind of these orange and like dark orange colors. So here, this is showing that this part of the fire, especially right here, but kind of all along this eastern side of the fire, because the fire radiative power values are higher, this is where that most intense burning of this particular fire was actually occurring. Okay, so it was kind of all along the edges here, and then particularly this part here that has the darkest shade. Okay. So there's a couple of different VIIRS fire products. So we're going to work with the one that's called Active VIIRS. It's abbreviated AF. And there's two Active VIIRS products. There's one that just uses the M bands of the VIIRS instrument, and that has 750 meter resolution. And then there's one that uses the I and M bands, and it has 375 meter resolution. This is the one that we're going to work with, okay? I made a note of it here. So it's called the Active VIIRS I band product. I stands for imaging. And so we're going to work with this one. It has the higher spatial resolution, okay? And it has some additional information in it that we can talk about next week, okay? All right, so this is the ABI product. Remember, we just downloaded the ABI product. It's abbreviated FDC. That stands for Fire Detection and Characterization. You might also hear the product called Fire and Hotspot Characterization, abbreviated FHS. I'm not sure why they have two names and two abbreviations, but if you see both of them, don't get confused. So the FIRE product is on both the GOES 18 and GOES 16 satellites. And it includes, so the full disk, which is what you guys care about, but it also has the CONUS and the mesoscale sectors. So if you remember from last week, the mesoscale, those are the high frequency every 1 minute or sometimes every 5 minute observations. So that started for FIRES in April of 2021. And then so what we care about is the GOES 16, the FIRE product, and that's been available since March 30th of 2018. Okay, and you can see Chris is planning to do, my colleague Chris Schmidt is planning to do some improvements to, basically improve the algorithm for the FIRES. And this was just a little example. So you can see these are the little pixels here. Hopefully you can see them in the middle of the FIRE being sensed by the GOES 16 ABI. Okay, and you'll notice there's this different coloring, this legend, okay, these 6 different categories. So let me just say a little bit more on this page. So, so the ABI FIRE product also has quality flags, okay, it's called the FIRE mask. So there's 6 quality flag categories. And honestly, I find them a little bit confusing. They have different names and they have different values, like the actual variable. So when we work in 2 weeks, when we work with the FIRES data, we're going to use this information. So you'll see how it works. But I just wanted to let you know that we're going to use what's called the processed and saturated categories. That's these 2 here at the top. These are the same ones that FIRMS uses. If anybody uses FIRMS, I think Anna mentioned it on on last week in her presentation. It's the FIRE Information for Resource Management System. And so this is also the recommendation from the FIRE science team. Okay, so if you don't want a lot of false alarms, which we don't, okay, we're going to use these 2 categories, these 2 quality flags to screen the FIRES data. Okay, and so again, we'll see how this works in 2 weeks. Okay, so just as a summary, so the fire radiative power is just a measure of the rate of radiative energy emission per unit time from all the fires within a pixel, so either an ABI pixel or a VIIRS pixel, and it's essentially it's an estimate of fire intensity. The VIIRS product is called active fires. We're going to work with the I-band active fires product that has 375 meter resolution. And in fact, the science team is trying to phase out the M-band product. So that's why we're using I-band. In the file, we actually downloaded those files last week. Both the fire detections and the fire radiative power are in the same file. Okay, so we only have to download one file and we'll get both sets of information. For the ABI product, it's called FDC, Fire and Detection Characterization. So it has 2 kilometer resolution. It's available for all 3 of the ABI scan sectors, but again, we just care about the full disk for South America. And you get fire detections and FRP in the same file. There's also a measurement of the size of the fire and the temperature of the fire. We're not going to talk about those. They have a lot of uncertainty, but those data are also available in the same file. Okay. And I think, yeah, that's all I have. So does anybody have any questions about AOD or FIRES, the level 2 products?
Amy,
Yes.
how did you get, I mean, it seems like the mesoscale product that you were describing before is obtained on request for some reason, like a lot of activity or something that is interesting in scientifically wise. I don't know. When there is this mesoscale data available, it's not all the time, right?
No, wait, hold on. I'm trying to find where did I put my website?
And it's only the US, right?
There we go.
Or not necessarily?
Not necessarily. Okay, so
Okay.
going back, so I mentioned this last week, but so again, these are the scan sectors. So we talked about the full disk. There's also the CONUS, right? We talked about that. And then there's these mesoscale sectors. And so the mesoscale sectors, they are adjustable. So they change every day. So these are the two default ones for goes east, which are the ones that are, relevant for South America. So Marco says, you're absolutely right. So when there's something happening, like there's a wildfire or there's a hurricane or there's severe thunderstorms or tornadoes, researchers will request from the GOES-R program to move the mesoscale sector over a specific location. And you can see they're small areas. They're 1,000 kilometers by 1,000 kilometers. They're not very big. And so if there's no requests, then the two sectors are going to be what you see here in the US, but they can move around. So I don't think they're in South America very often. Sometimes they're in the Caribbean because of hurricane formation, hurricane evolution. I would have to ask to see if they're ever in South America, but you could certainly put in a request, like if there was, something that was happening, and it was a quiet day in the continental US. I imagine that you would be able to have your request approved for South America. But if you're interested in that, I can find out exactly what the process is to request, because I'm not sure.
That would be great, because now we will have two simils in La Paz, one Pandora, and one simil in Santa Cruz, and two Pandoras, one in Santa Cruz and one in La Paz.
Mm-hmm.
So that means that it would be very interesting to, at least when we have a lot of smoke, like in September,
Right.
then to have these kind of things. Okay, fantastic.
Okay.
Thank you.
Yeah, remind me, Marcos, and I'll figure out, I'll find out what the process is of how you ask for that. Yeah.
Okay, I will. Thank you.
Okay, sure.
One question I had about the mesoscale products. So once they decide the region, it's for all the GOES products, right? Not just like aerosols or.
No, that's correct. Yeah, that's correct, Anna.
It's for everything,
it's that's where the satellite, the actual part of the ABI is scanning. And so it's all the level 1B observations, the 16 spectral bands, and then all the level 2 products, correct. Although again, not all of the level 2 products have a mesoscale product available. So for example, aerosol optical depth does not have a mesoscale file.
Okay, so of the products of interest to this for this webinar, then which ones? This is the fire detection?
Fires, yes.
Okay, but not the aerosol. Okay, that's important.
No, yeah, the aerosol optical depth does not have a mesoscale product.
Okay.
Ever.
Okay.
Yeah. So what we're going to do next, everybody, is we're going to move on to the week 2 Python tutorial. So we're going to use the same Google Colab application that we used for week 1. So if everybody could go to the Google Classroom, and on the home page, you'll see about halfway down, Amy Huff posted a new material, Python tutorial week 2. You can click on that there, or if you go up to the top where it says classwork, if you click on classwork, you should see under Semana Dos, the link to the Python tutorial. So again, if you click on that, I'm not going to do it because I already have mine open, but if you click on that, see, a new file should open up, and it will say at the top, week 2, create maps of satellite data using Python. Okay, and again, remember, everybody needs to, at the top of the file on the left, where it says file, click on that, and then save a copy in Drive. Anna, can you say that in Spanish, please?
Es importante ir a este paso que nos está indicando Amy, ir a File y luego Save a Copy in Drive. And this is so that their work is saved for next time, right?
Well, no, it's so that they can actually run and edit the file.
Okay.
So I think they can run it without doing this, but they can't edit it.
Sí, esto permite que se pueda cambiar el archivo, que se pueda editar.
Yeah. And it's also so they have their own copy as well.
y para tener su propia copia del documento. Okay.
All right, is everybody good? Okay. So, so at the top just has a little bit of background of what we're going to do. So today we're going to download a gridded AOD file, just because it's a quick and easy example. It'll give us global data in one relatively small file. So we're just going to go over how to open a NetCDF4 file, how to read the metadata inside, how to make a quick plot of the data using the X-ray package, and then how to select an appropriate color map for the satellite data. Okay, then we're going to cover basically two map backgrounds for satellite data. The first one is just what I call a shaded map background. It's just a simple figure with borders, land and water shading, and we'll see how to add latitude and longitude grid lines and labels. And then the second option is going to be a map tiles background. So we're going to work with the Esri World Topographic Map background and show how to actually add that to a figure, and then we can plot data over that. We'll do that next week. Okay, so the idea this week is to kind of go over some of the basics of working with data files and then working with maps. So that way next week we can focus specifically in on the VIIRS, aerosol optical depth, and VIIRS data. And then in week 4, we'll focus in specifically on the ABI, VIIRS, and AOD data. Okay, Marcos, did you want to, I saw you put something in the chat. Did you want to make an announcement?
Oh, just to, we have 3 people who haven't signed up for the classroom. So I am just asking them if they are in the class to do so.
Oh, okay. All right, great. So, so again, this section 0 is going to look very familiar. It's the same warnings as before. So I'm just going to scroll down. And so again, the first step is we have to import our Python modules and packages. We're using a slightly different combination. The main one we're adding this week is called CartoPy, and that's the Python library to make maps. Okay, so the very first thing we have to do again is we have to install the NetCDF4 package and the CartoPy packages because they're not included in the Google Colab configuration. So let's just run that first block to install those packages. That should just take a few seconds. Okay, and so then once that's done, we can scroll down and we can run this block now to actually import the modules and packages. Okay, and that'll just take a few seconds as well. Okay, and so just like in week 1, I'm going to make, last week, we made 2 directories. I'm just going to make 1 this week. So again, the same thing, we're going to make our new directory. And if you click on the little files icon, you'll see there's the new directory we made. It's called tutorial files. And then I'm just going to name the path to that directory just for convenience. Okay. All right. Is everybody with me? Okay. So this first, up until now, it's been very similar to last week. Okay. So like I said, we're just going to work with one. Oops, sorry, I went scroll too far. One data file today, and just to make it easy, because again, the point is going to be to look at some of these different packages. So I don't want to focus on the level 2 data yet. I want to wait until next week in week 4. So I wanted to download level 3 data file, which is a gridded file. And so in this case, the level 3 file is level 2 AOD, VIIRS AOD, that's been gridded at 0.1 degrees resolution. Okay, and these data are available from the STAR Online Archive. Okay, so what we're going to do is we're going to use the requests package, Python package. And so this is the URL, this is the web page where those gridded data are available. And then this is the specific file name of the file we're going to download. And so we're going to use, this is the requests package right here. This is where we're going to go get that, that file, and we're going to download it here. Okay, so if we run that, it should be very quick. And we come over to tutorial files, you should see that VIIRS 0.1 degree data set. And again, I'm just using that same case study day of November 6th, 2023. Okay. All right, does everybody do that okay? Anybody have any problems? That should be pretty easy. And then that's just another example too. If there are ever any information or data files that are available from a web page, you can use this same approach, this same technique with the request package to download those files. Okay. All right, so let's move on to section 1. So in this section, I want to emphasize that whenever you're working with a new satellite data set, the first thing you always want to do is open up the data set. Just open up one file and just look at what's inside. So understand what the contents of the file are, what the variable names are. For the variables, what are the valid data range? What are the units? What's the data types? So just make sure you understand what's in the file first before you try to start, actually working with the data. Okay, so we're going to do that. We're going to open the file using the Xarray package. Okay, and you can see I have some links to some of the documentation for the Xarray package. So let me just scroll down. So here we're just setting the file name. Again, this is the file that we just downloaded. And we're using the pathlib module to set the path to that file. So again, this is using the abbreviation for this tutorial file path that we just created, and then the file name for the file. Okay, so if we run this, and then here we're using the Xarray open dataset function to open that file. Okay, and we're going to use the netcdf4 package to open the file. And this DS, that stands for dataset, and that's just the name that Xarray has when you open a file. Okay, and the convention is to abbreviate it as DS. So if we run this, okay, everyone should see, let me scroll down here. So when you open a new file with Xarray and you print out the metadata, you'll see several different things, okay? So the first thing is I'm going to come down to the bottom where it says attributes. Can you guys see that? So the attributes are the global file metadata. So this is the metadata or the information about the file that's for everything in the file. So you can see, there's the name of the file. There's the, kind of the explanation. So again, it's the level 3 aerosol optical depth file. The resolution, it's 0.1 degree. The processing level, the instrument, the satellite. And these are specifically high quality AOD data. Okay. Remember we talked about the quality flags, high, medium, and low. This is just high quality AOD in this file. Okay, so the attributes are going to give you the information about the file as a whole, okay, as everything related to the file. Then if you come up, you'll see there's dimensions. So in this case, the dimensions of the file are the longitude and the latitude, okay, coordinates, which are right here. So for any of the coordinates or the data variables, if you click on this little icon that looks like a file, okay, if you click on that, see what I did? It'll open up the metadata for the specific variable. So, so this is longitude. So again, it's saying it's the center, the longitude of the center of each pixel, and then the units are in degrees east. Okay, and then the axis in this case. And if you click on this little icon that looks like a barrel or a server, maybe it's the data repository. You click on that. Often it will give you a specific sample of the data that are in that specific array. Okay, so again, you can see that this is a floating point number, 32-bit floating point number or float data. And you can see the beginning of the array is minus 179.95 degrees. And then the end is 179.95 degrees. So essentially this is going from minus 180 to 180 degrees longitude. Okay. So again, if you click on it again, it'll just close that up. So we can do the same thing with the latitude. We can see this is the latitude. it's in degrees north. We click on the little data repository, we can see, again, this is global data. So essentially it's going from minus 90 degrees to plus 90 degrees. Okay, and again, this is also these data are floating point numbers. Okay. So then we can look under the data variables. That's where typically, your actual satellite data will be located. So in this case, again, this is a level 3 file, so it's relatively small. So there's only a few data variables. So the one we're interested in is AOD 550. So again, if we click on the little icon there, it will show us the metadata for the AOD 550 variable. So again, we can see its aerosol optical depth at 550 nanometers. We can see units equals 1. That means there's no units. Okay, so if you see units 1, that means it's unitless, which we know, so that's good. The resolution, it's 0.1 degrees by 0.1 degrees. Here's the valid range. So if you remember from my slides, the valid range of the VIIRS and AOD data is minus 0.05 to 5. Okay, and then there's some other ancillary variables, but we're not going to focus on those. So we're just going to look at the LON, the LAT, and the AOD 550. Okay, that's really all we need from this particular file. Okay. All right, does anybody have any questions about that? Because that's important. You just want to make sure you can open up a file in Xarray and you can take a look at the metadata. Okay. Okay. So, sorry, one more thing. So if we actually click on for the AOD data, we click on the data repository. A lot of times you'll get something that looks like this. Okay, you won't actually. So you remember when we did the latitude and longitude, we actually got a little portion of the data array and it showed us what the values look like. So with a lot of times if you have a large array, it'll just do this. It'll just basically tell you how many values are in there and what the data type is, but it won't give you an example of the array. Oh, hold on, question. Okay, so Odon, I mentioned this in the slides. So the negative, so this minus 0.05, the very small negative values indicate the uncertainty in the AOD retrieval. Okay, so basically the calculation of the AOD with the algorithm. Okay, so you want to think about those very small negative values as essentially very small positive AOD values. Okay, they're just representing the uncertainty in the AOD retrieval. Okay, yeah, good question.
Which, Amy?
Yes.
Which in this case means that the uncertainty is in the order of 0.05, right? More or less.
Well, so I forget what so there's the requirements for the precision and the accuracy, and they vary depending on what the measured AOD value is. So and then they vary depending whether it's AOD measured over land and water. So the categories are something like, it's like AOD up to 0.3, and then from, I forget what it is, like 0.3 to 0.8, and then greater than 0.8. So and then the accuracy and precision requirements vary slightly for each of those categories.
But I guess it would be less than 0.1, for example, or around that number. I don't think it's going to be.
Yes.
Okay.
Yes. Yeah.
Let me just say something in Spanish.
Yeah, please go ahead.
Solo para clarificar lo que llamamos a veces en español el error o la incertidumbre de la medida, es lo que más o menos produce estos números negativos pequeñitos, ¿no? Significa que es 0 más menos la incertidumbre a algún número, pero que es pequeño. En el caso del ejemplo, menos 0.05, pero ahí me explicaba que puede llegar varía dependiendo si es sobre tierra o sobre océano, y pensamos que debería ser menor a 0.1, que es algo razonable. Nada más para aclarar la buena pregunta de que hace Odón. Gracias. Go ahead, Amy.
Okay, thank you very much, Marcos. Okay, so what I want to do is I want to see what the AOD 550 data, what they actually look like. Again, this is one of the steps that I do whenever I'm working with a new data set. I just kind of want to check what the values, how they're showing up in the array, what the units are, and what the valid range is. But, there's too many AOD values, so Xarray isn't showing me an example of the data array. So what you can do is you can use this function called xarray data array values, and that will actually display the data array as a NumPy array. So NumPy, for those of you who work with Python, NumPy is a package that allows you to work with actual variable arrays. Okay, it's very powerful. So if we run this, what happens is that the array, you get a snippet, basically the very beginning and the end of the data in the file. Now, the problem is that the data, the AOD data at the beginning and the end of this particular file, they're either not valid or they are missing. Okay, that's why they're abbreviated by this NaN. Okay, that just means the data are missing. So this isn't helping us very much, right? We still can't see what the data look like. So what you can do in this particular case is you can use NumPy, again, the NumPy package. So you can use the NumPy package to get the non-NaN minimum and the non-NaN maximum values in the data array. And so that will actually give us some numbers that we can see. So we can see in this particular case that the data are floating point numbers, which we expect them to be from the metadata. And we can see again that the range of the value, so the minimum value and then the maximum value, fall within that stated data range that was in the metadata. So that's good. That's what we expect, and so we can confirm that, and so everything is the way it should be. Okay. Does anybody have any questions about that? Okay. Okay. So another thing that is helpful to do often is if you're working with a new data set, just to make a quick plot of it before you actually try to go on and either analyze the data, or if you're going to make a map of it, to do that, just to kind of quickly see what the data look like. And xarray has some really basic built-in plotting functions that can help with that. And so this is what the very basic plotting function looks like. So it's the data array name and then just dot plot. Okay, so if we run that, we're going to get a very simple, very basic plot of the AOD data in this file. And again, remember, it's global AOD data and it's high quality AOD. Okay, so again, it doesn't look that nice, right? It's not particularly formatted, but it is at least giving us an idea of what the data in the file look like. Okay, so again, it's basically latitude and then longitude. Okay, now before we go on, I want to actually talk a little bit about how we display the data. Okay, so the default color map, which is this choice of colors that are assigned to values, the AOD values. So this is called a color map. And so the default color map with xarray, you can see it's what's called a diverging color map, meaning that it's centered at 0, and then there's a different set of colors for negative numbers and positive numbers. Okay. But the problem is that most AOD data, most satellite data, and that definitely includes AOD, they're not diverging, right? They're sequential. So they essentially start at 0 and then increase in some sort of positive, usually positive value, right? So we saw that the data range is going to be basically from minus 0.05. So essentially from 0 to 5. Okay, so we don't want a diverging color map. We want to pick what's called a sequential color map. Okay, so that essentially, it's one color that starts at 0 and then it changes as your values of AOD increase. Okay, so in the next section, basically what we're going to do is we're going to use any of the built-in color maps from the matplotlib package. So matplotlib is Python's plotting package. So any sort of data plotting that you want to do, matplotlib is the package that you use. Okay, so if you click on this link where it says built-in color maps, and then you have to click on this link again to leave Colab. So this will open up the matplotlib documentation. And if you scroll down this page, it talks a little bit at the top about the things to choose when you're considering a color map. But if you keep going down, it'll give you examples of the available color maps. And so we want to pick something that's under this sequential heading. Okay. So again, you can see the how the sequential color maps work. So they start basically with one set of colors and then they change like that. Okay. Instead of being, again, the diverging ones, essentially, they're set at 0 and then they increase both or decrease both ways. Okay. So any of these sequential color maps here, so there's these ones, all the colors, and then there's some more down here. So I picked rainbow, which I forget where rainbow is, but I think it's a little bit further down. But I picked rainbow because I like rainbow, but any of these would be fine to pick for most satellite data. Okay. So if we go back to the training tutorial, you can see that now we're going to do the same thing. We're going to make that quick plot with X-ray, except now we're going to add this argument where we're going to select the color map. Okay, so if we run this, it'll take a second. Okay, and now this is a little bit better, right? Okay, so instead of being those like kind of murky, like tan colors, now at least we have a sequential color map. But there's still a problem, right? Almost all of the data are shaded a green color. They're showing up on the plot as almost the same color. Okay, and one of the reasons why is we can see the range of the color of the plotted data is going from -5 to +5. Okay, but again, we've talked about this, right? The actual AOD data, they essentially go from 0 to 5. So we need to change the range now of the plotted data so that we don't have all of these colors assigned to negative values, which there's never going to be any on the plot. Okay. So in this next section, let's change the range of the plotted data. So again, this is the same simple plot command, okay? And we're going to pick this same color map, but now we're going to set the minimum value and the maximum value of the plotted AOD data. And you might be asking yourself, well, why are we setting the maximum to be 1 instead of 5? Because we know that the actual range of the data goes up to 5. And the reason why is because most of the data, if you come back up here, this green shading, most of the data are clearly in this like 0 to 1 range, okay, where this like greenish shading is. So that's why we want to set the range around 1. So that way we'll be able to really, the whole color map will show the range of the data. Really, the dynamic range of it will show up nicely. So let's do this. And then I think if you see it, it'll make more sense. Okay, so see now how this looks a lot better. So we've set the range of the plotted data from -0.05 to 1. Okay, so we see this little arrow on the end. So we're still plotting the data that are between 1 and 5, okay? But they're showing up as this red color, the same color as AOD equals 1. So now we can see that most of the data, AOD data, are pretty low values, like somewhere around, between 0 and 0.1. That's this kind of lighter blue color. And then there's some areas that are maybe around 0.4, 0.5, is kind of this green color now. And there's a couple areas, one of them is in Bolivia and northern South America, that are red. And then also this is over in India and part of South Asia that have really high AOD values, either around 1 or greater than 1, okay? So the next thing we want to do is, we actually wanted to highlight any AOD that is greater than 1. Okay, right now it's the same color, it's this red color, but we can change the color. We can pick a unique color for any of the AOD values that are greater than 1 up to 5, and then make them really stand out on the map. Okay, so let's do that next. Okay, so that's this section. So you can see I've put a link into the list of the Matplotlib package built-in colors. They have a whole range of colors. So you guys click on this, it's going to open up again another tab. You click on that. So it's going to go back to the Matplotlib documentation. And again, this is the information about the colors that are in Matplotlib. So again, if you scroll down, so here's all the colors. So there's just some basic ones. But then here's all this lovely list of all these different colors that you can use in Matplotlib. Okay, so the one I picked is dark red. Where is dark red? Right here. Right here. I guess I can't highlight it. It's right here. It's this dark red color. Okay, but in a second, you're going to get to pick your own choice of colors. All right, so if we go back to the code, so now you can see what we've done is with our color map. So we have some slightly different commands. This is a Matplotlib package command. So we're still getting our rainbow color map, but now we're going to say any extremes, meaning anything that's over this Vmax equals 1, we're going to color it dark red. Okay, so if we run this now, okay, so now if we run this, now things look nice. So you can see in the color bar, the top arrow is this dark red color. So the range of the color map is going between, the full range of the AOD data, and then anything over 1 is this dark red color. So it's really going to be standing out. So it'll draw our eye to where the areas of the thickest aerosols are. Okay. So this is essentially what I want. I mean, hoping everybody will think about if you're working with a new satellite data product. You want to think about what's the most easy to communicate, easy to understand way to plot the data, so that when you're looking at it, or you're sharing it with the public, or you're sharing it with your colleagues, that the data are easy to understand. Somebody can look at the plotted data and really interpret it quickly and easily. And a lot of that has to do with how you choose to represent the data in terms of the color map and the data range that you use. Okay. All right. Does anybody have any questions about that? That's an important point that I wanted to make. So basically, don't just use the default color map that Xarray or that Matplotlib give you. Really think about it and make a choice that makes the most sense for whatever data you're working with. Okay. All right. So in the next step, I want you guys actually to make this same plot that I just made, but actually pick your own color map and your own color for AOD greater than 1. Okay. So again, go pick, here's your list, all the list of colors. I gave you the link, and then all of the different color maps that you can pick. And if you scroll down, there's more. And I think if you go past the diverging and the cyclic, yeah, under miscellaneous, there's some more. So take a look at all the different color maps and colors, and just make a quick plot of AOD 550 like this. But try a few different color maps, try a few different colors, see what combination you think works best, and communicates the AOD data clearly. So I'll give people a few minutes to try that.
Y si tienen alguna pregunta, pónganla en el chat, por favor.
Okay, did everybody get a chance to try something? So I forget what I picked. when I was doing this. Let's see what I picked. I think I picked shades of brown. Oh yeah, I picked, because I've been told that the rainbow color map is difficult for anybody that has color blindness to interpret. So NOAA likes shades of brown. So that's why I picked these different shades of brown. And then I like pink, so I picked bright pink for the AOD greater than 1. Okay. But again, basically you see how all you do is you pick your color. Oh, I forgot to mention, if you add _R to the end of any color map name, it will reverse it. Okay. So if we go back over the color maps and we find where pink is, it's right here. Right here. So see how the pink color map actually starts with the darker colors and it goes to the lighter colors. So by reversing it, I made it go from the lighter colors to the darker colors. Okay, which I think makes more sense intuitively for the AOD. We want to highlight the higher values of AOD, not the lower values. Okay. All right, does anybody have any questions? Yeah, color maps are very important. Okay, great. Okay, so the last part of this section I just wanted to highlight is, you know, eventually we're going to make like real nice map plots of the satellite data. Okay, we'll do it a little bit later in this tutorial, but particularly next week and the week after, we're going to be making a lot of different maps of satellite data. So for each map we make, you know, anytime you plot data, you want a title for your plot, right? You want to have information in the title of the figure so that, you know, when somebody's looking at it, they can interpret, they understand, you know, what that plot is showing them. So for each map we make, we could manually make a plot title, okay, with like the satellite name and the sensor and the observation date and time. But anytime you do something manually, of course, it's prone to error and it's also quite tedious. So what I like to do is actually use the information in the satellite file name to generate a title for my plots, and then also a name for the file when I actually save the image file to my computer, or to, in this case, to the Colab instance. So I just wanted to show you how to do that. So what we're going to do is we're going to use the Python string split type, and we're going to use Python slicing. Okay, so anybody who's not familiar with those, I'll show you how that works. Okay, so down here, so the first thing, let's just print the file name again so you can see. You know, again, this is a gridded file, so it has a different format from the level 2 files that we looked at last week and then this morning, but it has a lot of the same information. So, you know, it has the sensor name, which is VIIRS. The EPS stands for the enterprise algorithm, which we talked about earlier today. NOAA 20, so it has the satellite name. In this case, it also has the product name, AOD. So this is a level 3 file, so it has the resolution of the file, which is 0.1 degrees, and it has the observation date, which is November 6, 2023. Okay, so we can pull those pieces of the information out, and we can reformat them and use them to make a title for our plots. Okay, so basically that'll include automatically, it'll include the resolution of the file, the dates, and then the satellite. Okay, because it could be NOAA 20, it could be NOAA 21, it could be SMPP. Okay, so let's just see how we do that. So, so I should mention, Python has, where did it go? It's up here. So this is part of the pathlib module. If you remember, we're using the pathlib module to set our file system paths. If you append .name to any pathlib object, then it returns a string that represents the final component in that path, in that directory path. In this case, it's the file name. Okay, so that's what we're doing here. So we're doing file ID.name. So remember, way back, like up at the beginning, we set the directory path to this file on the Colab instance. We defined it as file ID. So when we append name to that, it returns the final component, which is, in this case, it's the file name. Okay, so that's what we do here. It's a little bit of, it's like a little trick. One of the aspects that's nice about the Pathlet module. Okay, so we're going to repeat that again. So we're using the string split built-in type. Okay, so basically we're going to split this file name using the underscore. Okay, so essentially what this is doing, and then this 2 afterwards with the brackets, is saying grab the second piece of the file name that's split by the underscore. The only thing is you have to remember that with Python, counting starts with 0. Okay, so that means so we're splitting with this underscore. So so this is 0, this is 1, and this is 2. Okay, so we're getting that whole thing, that NOAA 20. Okay, and we're saying if it's equal to NOAA 20, we're just going to reformat that. I'm just going to capitalize the NOAA, okay, and put a little dash, and that's going to be the name of our satellite for our plot title. Okay, and then we're going to do the same thing now to grab the resolution of the file, which is 0.10 degrees. We're going to do the same thing with the actual date, right? Except we're going to do a little magic. We're going to use the date time module, and we're going to take the date, which is in year, month, day format, and we're going to turn it into, you'll see when we print it out, but basically I put it up here. I like to reformat just to make it something that's a little bit easier to read in a plot title. So in this case, it's going to be the day, an abbreviation for the month, and then the year. Okay. And then we're going to put it all together. We're going to put all the pieces together to make our title. Okay, so if we run this, you'll see, so now this automatically generates, this is our title. So it's got our satellite. We know that's always going to be VIIRS aerosol optical depth. We've got the resolution of the file, and then we've got the date. Okay, and so we generated that all automatically so that first of all, we don't have to think about it. It's easy. And then secondly, we know we're not going to make any mistakes because it's coming right from the file name. So we're not going to, mistype anything if we're trying to do it manually. Okay. So anybody have any questions about that?
Yeah, I'm just going to repeat.
Okay.
The title, by title, you mean the name of the file, right?
Where, down here, Anna?
Yeah, at the end.
No, that's going to be, so we're going to do the name of the file, but in this case, it's going to be the actual, so when we make the figure, it's going to be at the very top of the map figure, basically showing, actually, I probably have an example here. Hold on.
Okay, yeah, I think an example would help, but yes, yeah.
It's going to be this. This is what we're going to make, Anna. It's this right at the top. Do you see that?
Entonces, cuando ella está diciendo de plot title, se refiere a lo que va a salir en la misma figura, en la parte de arriba. Lo que es las palabras indicadas aquí, ¿no? El nombre del satélite, el parámetro, etc.
So, Odon, that's what we're going to do next. Yep. Well, actually, we're going to do a couple other things, and then eventually we're going to make this plot right here, which is, well, it's not just over South America, but it's just over the Western Central South America. So I'm going to be showing you how to do that in a few minutes. Okay. Any other questions? That's a good question. So basically, I'm trying to show you the kind of the pieces, like the steps that we have to take along the way to make that figure. And then at the end, we're going to put it all together. Okay. Okay. All right. So let's move on to section 2. So I can where did I put the figure away? Let me bring it back up again. Okay. So, oh no, I guess I didn't have it away. So what we're going to do next is, so eventually we're going to add the satellite data, but what we're going to do next is we're going to see how to actually make this background where we have the shading for the land. we add the borders, we add the latitude and longitude grid lines and labels. That's what we're going to do in this next section. Okay. So,
Amy, you have a question
yeah.
on the chat. In English.
Oh, I just answered that, right?
Oh, sorry.
So so that figure that I just showed, we're gonna make that. I'm gonna show how to make the map background, and then we're gonna make that plot. So that the answer to Odin's question is coming up. Yeah, thanks, Marcos. Okay, so section 2. So we saw, that X-ray, that kind of basic plot that we did. It's fine to just check and see what a data array looks like. But if you actually want to make, a real plot, something that looks nice, then you need to use the cartopy package. And then we'll also talk about some other settings in the matplotlib package. Okay. So, the cartopy package, this is where you actually pick a map projection, where you set up the map. And cartopy has many, many different map projection options. So I'm gonna open up this page and just show you. So this is the list of all the different map projections, and you can see them on the right here. So all of these here, those are all different map projections that you can pick. Okay, so we're going to take a look at 3 of them, and then you're going to get to pick one of your own. Okay, so let's look at 3 different ones, just so you can see how you select a map projection and what some different ones look like. All right, so the first example is what's called the plate carré projection. So it's a equidistant cylindrical or equirectangular projection. Okay, and so the way we make a map in Python is we use the matplotlib package to set up a figure. Okay. And then we add what's called geoaxes here using the map projection. So this part right here is where you set the map projection. Okay. So in this case, again, we're going to start using the plate carré map projection. And then we're going to add coastlines just so you can see like what the Earth looks like in this particular projection. And then this just shows the plots. Okay. So if we run this, oh, and you'll see this warning message, okay? That's nothing to worry about. Every time you download or you use a shapefile from cartopy, has an interface to the natural Earth feature shapefiles. So the first time you use it, in this case, we added the coastlines. We downloaded this coastline shapefile, okay? So, but I guess Python just wants you to know that you're doing that, but just don't be troubled by that warning. Okay, that's all that it's for. All right, so you can see this is what the plate carré map projection looks like. Okay, it's equidistant rectangular. Okay, so let's look at another one. So this is called, I think it's pronounced molvita. So it's a pseudo-cylindrical equal area projection. And so this code is exactly the same. The only thing that's different is here where we set the projection. When we add the geoaxes, we've just changed it to the molvita projection. Okay, so if we run this, you can see what that looks like. So yeah, so see, that's kind of like if you're working with a global data set, that's kind of cool. I think it's kind of neat. And then I picked one more. So this last one I picked is called the interrupted good homosoline. It's a composite equal area projection. It kind of looks like if you peeled an orange and laid the peel out. So again, the only thing that's different is here where we're setting the map projection. And this one has some arguments. So we're actually going to emphasize the land, but if you wanted, you could emphasize the ocean instead. So see what that looks like. See, it looks kind of like an orange that was peeled. At least that's how I view it. And if you wanted to emphasize the ocean instead, here instead of land, you would just type ocean, and it'll show. And again, so it's kind of peeling the orange in a slightly different way. So it's emphasizing the ocean areas instead of the land. Okay. Okay. So now exercise 2. I want you to basically do the same thing. Just make a global map, without any satellite data. and just pick a different map projection. So go to that list of the Cartopy map projections, and you can kind of just scroll through and, you know, maybe pick one that looks of interest to you, and you know, basically see what the argument is. For this case, it's Mercator. And just come back here and just make your own map figure using your choice of map projection. Maybe try out a couple, just, you know, see what they look like. I'll give people a second to do that.
Si nos pueden indicar en el chat o con algún gesto o el thumbs up o como vean si han podido llegar a donde estamos ahora y si todo va bien o tienen alguna pregunta. Gracias.
Oh, I forget how to spell Mercator. Mercator, yes. Okay, everyone's okay? Okay, great. So I decided to use the Mercator. And so one thing I want to mention, if you go back, here's the Mercator. This is what it looks like, okay? So the default central longitude is 0, the prime meridian. You can change that, okay? So you can use, you see for each of the map projections, they have these various arguments and they're defined down, you know, they call them parameters, but they're arguments. So in this case, it's the central longitude. It defaults to 0, the prime meridian. You can change that. So let's say I changed it to 180 degrees. So the international date line essentially instead of the prime meridian. So when you do that, you can see it basically just splits where the edges of and the center of your map is. Okay, so just be aware that as you're looking through that Cartopy map projection list, you can modify the map, you know, in different ways to make it appear the way you want. Okay. Okay, and then this is the Mercator projection. Okay, great, and it looks like a lot of people were able to do that. Okay, so now, so this is going to answer at least partially Odin's question. So, you know, up here we've got these global maps, right? But you guys are interested in South America. You want to zoom into South America, right? You don't want to see all the rest of the map probably. So the way we do that is we have this function called set extent, okay? And then we have four numbers here that correspond to the latitude and longitude coordinates, okay? So it's going to be the western longitude, the eastern longitude, the southern latitude, and then the northern latitude of the edges of the zoomed in geographic domain where you want the map to be, okay? So in this case, I picked from -78 to -53 degrees longitude, and then from -26 to -8 degrees latitude, okay? So, oh, and again, it's gonna, so now we've zoomed in. So Cartopy has just downloaded another shapefile for the higher resolution coastlines. Okay, that's all that happened there. So now you can see, this isn't super informative yet, right? Because we just have the coastlines, but at least you can see now we've zoomed in and we've got that western, kind of central western coast of South America. Okay, so anytime you want to zoom in, this is the function that you need to use. Oh, and I forgot to mention, so this is obviously, this is where you're setting the actual boundaries. You always need to add this second argument, this CRS equals CCRS plate carré. And this plate carré, this doesn't have anything to do with the map projection, okay? It's a little bit confusing. So up here is where we're setting the map projection. They just happen to be, it happens to be a plate carré map projection, but we could change this. I could make this Mercator and do that. Okay, and run it. Okay, so this plate carré, this always has to be there, okay? And the reason why is because this plate array is telling Cartopi that these coordinates are in latitude and longitude, okay? So just be aware, this is always going to be here, okay? And it's completely separate. It's different from this part up here where you set the map projection, okay? Can you maybe say that in Spanish, Anna? Because that can be confusing.
Okay, can you repeat again what you want me to say in Spanish?
Yeah. So in this line of code right here, this is where we're setting the geographic domain, the latitude, longitude corners for our zoomed in area.
Mm-hmm.
This line right here, that where I've highlighted, that always has to be there. That never changes. Okay. And it's what it's doing is it's telling the package that these values are in latitude and longitude. Okay.
Vale, entonces
So I have it.
esa parte, lo que tiene ahora mismo en azul, eso que se ve, eso no se cambia. La única parte que sí se cambia son, son los números donde pone menos 78, menos 53, 26, 8, que son las longitudes y las latitudes, que se van a, que van a salir en la figura. Son los cuatro puntos de latitud y longitud.
Tal vez solo decir que la instrucción esta, que está subrayada le indica al Python que esas son coordenadas en latitud y longitud.
Yeah, we're going to see this again too. When we actually plot the data, we're going to need to actually include this again as well.
Okay, Javier wrote CRS is the projections.
Yeah, CRS stands for Coordinate Reference System. Okay. All right. Is everybody good? Okay. Because so let's fill in this map, right? Because this isn't very informative. Okay. So let's add. So Cartopi has a lot of different options, actually, like 3 or 4 for adding borders and international borders, state borders, shading different land and ocean areas. I like the Cartopi feature interface. Okay, if you link here, it'll give you more information. So if we scroll down, here's some examples of the Cartopi feature interface. Okay, so you'll see everything else up here is exactly the same. Okay, this is the part that we're adding. And so we're adding coastlines, which we already had, but this is a different way to add them. We're adding international borders. We're adding large lakes, the land, and the ocean. Okay, and you can change the width of the coastlines and the borders. You can change their color. You can change the color of the land, lake, and ocean polygons. So we're going to color the lakes and the ocean light blue. And again, these colors come from the list of the Matplotlib colors, which we saw earlier. And we're going to color the land wheat, okay, which is like a brown color. So if we run this, and again, so now we're downloading for each one of these features, we're downloading another shapefile. So again, don't let these warnings, the first time you download the shapefiles, you're going to see those warnings, okay? So now, now this looks more like a map. So we see where the ocean is. We see, a large lake here and here. We can see the borders of Bolivia, for example, and Chile and Peru and Argentina and, I forget what that is, Paraguay, I think, and Brazil. I apologize for my poor geography. So basically using the different settings in Matplotlib and Cartopi, you can make this map look however you want, okay? I think that's fun. I don't know. I always get excited. You can spend a long time tinkering with maps to make them, look exactly how you want. Okay, so now let's, another nice feature is if you want to add latitude and longitude grid lines and labels. So Cartopi has something called the grid lines function. And again, if you click here, it'll give you more documentation. And then there's a tutorial actually that I've linked to here if you want more examples. But the way to do that is, again, so we have everything is the same up to here, and then here's our coastlines and borders. So this is the new part, okay? So we're adding right here, whoops, right here is where we actually add the grid lines, and then draw labels equals true. That adds the latitude and longitude tick labels on the outside of the map. And so you can change the width, the appearance of the grid lines. So I'm having, you know, relatively narrow lines, not too narrow, and I'm going to color them navy. And then you can change the appearance of the line. So I'm going to use dash lines. That's what this does right here. You could also have a solid line or a dot dash line. Okay. What this part does is this actually sets the intervals for the grid lines. And I personally like to set them myself. So, and this is where we do it here. So this is where we're defining where the intervals are for the longitude tick marks and lines, and then the latitude tick marks and lines. The default is to plot the labels on all four sides of the map, but I think that's too busy. So I don't plot them on the right or the top, but you know, obviously you could modify that. And then I like the labels to be a little smaller than the default. So we're going to set them to be 8-point font. Okay, so if we run this, so you see how that added. So here's our grid lines. Okay, they're navy and they're dotted lines. And then again, we have our labels around the left side and then the bottom of the plot. But obviously you could change that. You could have it just be on the right and the top. You could have it on all four sides. You can spend a lot of time modifying the appearance of maps so that it's whatever you want it to be. But I just wanted to show some examples, you know, basic examples of the settings so that you can make the maps look like how you want. Okay. Does anybody have any questions about that? Okay. All right. So now let's completely answer Odam's question from earlier. So now we're actually going to plot the VIIRS gridded AOD, and we're going to plot it on this map domain right here. Okay, this zoom in area of Central Western South America. What I'm going to do though is I'm going to change the background. So instead of being this brown and blue, I'm going to make it shades of gray, just because I want to have a neutral background when I plot the satellite data. I'm going to use that rainbow color map that we used earlier. Okay, so I want to have a neutral background so that I can really see the satellite data. But if you picked a different color map, you know, when you're working on your own research, you probably are going to want to pick, you know, shade a different color for the background, something that's appropriate for your color map. Okay, so a couple things. So this is our plotting code. So you can see everything up to this point is exactly the same, right, as what we had just done. So we're setting up our figure. We're adding our geo-axes. I kept with plate carré. You could change this if you want a different map projection. We're zooming in to Central Southern South America. We're adding our grid lines. So again, I changed the color to silver. Again, so the grid lines are going to, you know, they're not going to contrast with the satellite data. Here, we're adding the coastlines and the borders. Like I said, I used colors of light gray and gray to provide a neutral background. So here's our color map, exactly the same code as we used before. So right here, this is where we're plotting the satellite data. Okay, we're using the matplotlib p color mesh function. Okay, and Xarray makes it really easy to plot the data from the file. So all we have to do is pull out, if you remember, when we opened the file, we opened it as a data set, which is abbreviated as DS. So all we have to do to get to any of the data arrays is just do DS and then the name of the array. So this is the longitude array, that's the latitude array, and this is the AOD 550 array. Okay, and we're using that color map. We're going to plot the AOD from 0 to 1. like we talked about. And then we have to include this argument right here. Again, this is going to look similar to what we talked about before. Anytime you have geographic, or your data that's in geographic coordinates, like latitude and longitude, which the AOD is, you have to include this argument, okay? It's separate from the map projection. This is always going to be there. If you don't have it, then the satellite data won't plot correctly, okay? Then we're going to add the AOD color bar right here. We're going to add, remember we made that plot title, we're going to add it here. We're going to show the plot, and then we're going to actually write down here, we're going to save the file, the plot that we make. We're basically using that same approach. We're going to take information out of the file name, the data file name, and we're going to use the matplotlib.savefig function. And so we're going to save the image file using that name to the tutorial files folder that we made. Okay, and then we're going to close the plot. Okay, that's a lot. Let's run it. And if anybody has questions, they can ask me. Okay, there it is. Okay, there it is. And if we come back over here, we'll see. Let me make this a little bit bigger. We'll see this is the map file that we just made. So it's a PNG file. You could make it a JPEG if you wanted to, or there's other file formats in Matplotlib. But this is our file here. Okay, and let me make that narrow. So again, this is what it looks like. It's probably easier if I already downloaded one. I can look at it in full scale. So again, you can see we have our labels, our latitude and longitude labels. I changed the background to be this light gray for the water and darker gray for the land. Our borders are black. The grid lines are solid, and they're like a slightly darker gray color than the ocean. And then you can see the satellite data. So you'll notice that the satellite data, they look like pixels, okay? And again, this is because this is the level 3 data. It has 0.1 degree resolution. So it's going to look a little bit, it's a little bit coarser resolution than the level 2 product that we're going to work with next week. Okay. So did everybody get that to work? Make that plot? Oh, Odin, thank you. Excellent map. Thank you. So that is that what you wanted to do? Did that answer your question, Odin? Yes. Okay. Fantastic. Fantastic. All right. All right. Thanks, Marcelo. Okay. All right. Everyone seems happy. Oh, Anna. Oh, okay. Okay. So, question, Javier. The 0 and 1 values. Okay. So, Javier, do you mean the 0 to 1 in the color map down here? Okay, I'm going to assume that this is what Javier is referring to, the 0 to 1. So this is the actual value of aerosol optical depth. So if you remember from the slides and from the metadata when we looked at the file, AOD doesn't have any units, okay? So that's why there's no units here. And so remember that the aerosol optical depth, it goes from minus 0.05 all the way up to 5. But most of the data fall within the range of 0 to 1. So that's why we set the range for the plotted data from 0 to 1. So the colors that we see in the color map that we picked show the range and the gradations in the data. And then remember, we picked a special color. I picked dark red for any of the plotted data that are greater than 1 up to 5. 5 is the maximum AOD value, okay? So we can see that here. That's this dark red. Hopefully people can see this. Dark red shading in Bolivia, and that's corresponding on this particular day to very thick smoke, okay? Okay, Gabriel, is there a chance of AOD data getting confused by clouds? So AOD data, they don't get confused by the clouds. Anywhere there's a cloud, there's no AOD data, okay? So any place that you see gaps here, most likely those are because of clouds. Ana Prados, could you please translate the question from Ana Maria?
So then the closer to 1, the greater the concentration of aerosols, right?
Yes.
Sí.
That is correct. Yes.
Sí, y si excede el 1 es una concentración muy, muy alta de aerosoles, y que estaría también indicado por el color rojo y que puede ocurrir, ¿no? El rango es de 0 al 5, como ya nos explicó antes.
Una cosa más, a ver, no se olviden que esto corresponde, no es en superficie necesariamente, ¿no? De hecho, casi seguro que no es solo en superficie.
Okay, so we have 5 minutes left. This next section is very quick. So the first thing, let's just close that file we opened. So anytime you open a file, a data set, anything, you want to make sure you close it when you're done with it. Okay, that's just a good practice. So let's close the file or the data set we opened with Xarray. And so this last section is really quick. It's just, I think, two sections of code. So if you have you have aerosol optical depth, this kind of 2-dimensional data, having the plain background for the map, to me, I think is the best choice. But remember, if you have fire data, okay, those are points. They're individual locations. So plotting them on a map like this isn't very informative. So what I like to do instead is make an actual, map. It's called map tiles background. So something that basically has all the cities and the roads and the topography. So that way you can really see where the fires are in relation to urban areas and mountains and parks. So Cartopy has let's get through it. So Cartopy lets you basically add what are called tiles, image tiles. And so if you click here, you can read more about it. And there's a short tutorial. So I'm just going to do one example. I like the Esri World Topographic Map tiles. They're freely accessible. We have to give attribution, but they're free and they look nice. Okay. So the way we set that up is here. We actually link, this is the URL that will connect us to that map tiles. And then we're going to add this attribution to our maps. Okay. Because basically we just need to use to acknowledge Esri and all the data sources for the map information. Okay, and then we can use Cartopy right here to go and grab those map tiles. So if we run this here, okay, so now we've got our map tiles. So now what we're going to do is we're going to put them in a figure. Okay, so we're just going to do the global figure first, and then we're going to zoom into South America, just like before. So we're going to do the same thing. We're setting up a figure. We're adding our map projection. The difference is that you want to actually use the same map projection as the tiles image. And that is just makes things look the best. Okay. So don't change for the map background, don't change this map projection. Okay. Have it be the same as in this case, it's the Esri World Topographic Files. Okay. And then one thing we have to set is the zoom level for zooming in on the map tiles. So it goes from 1, I think, to 24. So 1 is the widest view. So we're going to start with 1. And then we're going to use the matplotlib add image function. So we're going to add that map tiles image. And then we're going to use the matplotlib anchored text function to add that attribution. Okay, so if we run this, so you see now, this is the Esri global map background. Okay. So isn't that kind of cool? I think it's cool. Okay. So now let's zoom in on Western Central South America. Okay. So we're going to do, it's exactly the same code, and we're going to use exactly the same command as before to set the extent of the map. Okay, the only thing different we're going to do is for the global map, we set the zoom level to 1. Now let's set it to 6. We have to set it to a higher number because that essentially is controlling the details of the map. Okay, so the resolution or the scale of the map. So if we run this, so now you can see this is how we've zoomed in now to the area around Bolivia. And so you can see, you know, with this particular map tiles, you get the city locations, you get some of the topography, like from the Andes Mountains, from the different plains and the lakes, and obviously the international borders. Okay. So we're out of time, but on your own, I want you guys to basically remake this map, but to zoom in a little bit more and then a little bit less. Okay. All right. There's questions.
Okay. There's a question.
Okay.
We're in Peru, in the area of Moquegua. I always see over a mining area that it's red color. Could that mean that the source is the mine, the source of the aerosols? I mean, it's hard for us to say, right?
Right. Yeah, I'm not sure we could say without more information.
Yeah. No podemos decir sin tener más información. ¿Se refiere a que el aerosol optical depth es color rojo en la zona esa? Porque hay que asegurarse también que no sea un artefacto, ¿no? Por lo que dijimos antes de que el aerosol también a veces tiene una anomalía en las zonas de montaña. Pero, ¿sabes? Si hay otros focos de aerosoles cerca de la mina, también podrían contribuir, depende. Lo que siempre recomendamos en este caso también es confirmar, ¿no? En caso de duda, con algún instrumento de tierra, si está disponible, confirmar que es una zona de aerosoles alta, si está disponible. Pero también nos puede mandar un email offline, a mí o a Marcos, si quieres, Leonel. Y también quería comentar, I'm going to talk about the homework, que la tarea número 1 que...
Yeah, and can I just say one thing before? So I just want everybody to remember that anything you download or create, like our file where we made the map of the AOD, it will be reset and lost. So if you want to keep this map, the map file, so you can either come over here and there's these 3 little dots. If you click on them, it'll say download, okay? Or if you up here, this little icon, it says Mount Drive, that will actually allow you to connect your Google Drive to this Colab instance and download the files that way. A third option is there's code here. If you run this code, it will open up a window and let you download this file to your local computer. Okay, so if you want to, my point is, if you want to save this file, this PNG file that we made, just make sure you download it before you close out this file today. Okay, all right. Thanks, Anna. That's all.